what I would like you to get out of this video is just an understanding of what happens when you put capacitors in parallel, and then also what happens when you put capacitors in series. I don't expect you to be able to reproduce these measurements or these calculations. This is just to help you understand maybe why this is true. So for a parallel plate capacitor, the capacitance is epsilon naught times the area of the capacitor divided by D. A parallel plate capacitor looks a lot like what is drawn here. So the symbol for a capacitor is two plates with wires connected to each one. So you can really think of these capacitors in parallel as being three parallel plate capacitors, and the distance, when you add plates or add capacitors side by side, you're not changing the distance between the plates, but you're adding more plates. So essentially you're adding more area. So actually the areas all add up. So as you increase the area, the capacitance will go up. So the equivalent capacitance of these three put together is just epsilon naught times, instead of A, the area of all three of them put together divided by D. So the equivalent capacitance seen by the battery is the capacitance of all three added together. That's what happens when you put capacitors in parallel. This is backwards from what you had with resistors in parallel. This formula looks a lot like the resistance in series. Now when you put capacitors in series, again, what you've got, this is a good representation, two plates with a gap in between them, and then the wires now go from one plate here to another plate on a different capacitor. Now if you're going to store charge on these capacitors, then if I need to get charge onto this plate, there's only one place it can come from. It has to come from this plate here. So if the capacitors had zero charge when you put them together, and then you put in a battery that starts to charge one of these plates, if the other plate's going to be charged, and the two opposite plates always carry the equal but opposite charges. So if you put 100 nanocoulombs on one side, you'll get negative 100 nanocoulombs on the other side. That negative 100 nanocoulombs had to have come from this plate. So however much you charge this one, C1, C2 will have the same charge, Q. And similarly, the charge here had to have come from there. So capacitor 3 has to have the same charge as capacitor 2 and capacitor 1. Now, capacitance is charge per volt, which if I rearrange it just means the voltage is charge per capacitance. So the voltage on a battery is, by Kirchhoff's loop rule, if I loop around here, the voltage on the battery has to be equal to the voltage here plus here plus here. So the three voltages add together. The voltage on C1 is Q over C1. Then voltage 2 is here, voltage 3 is there. So the same Q all three times, but three different capacitances. So if I just factor the Q out of that, I see that V for the battery is just Q times the 1 over C plus C1 plus 1 over C2 plus 1 over C3. So the voltage is charge per capacitance. So voltage on the battery has to be the charge divided by the equivalent capacitance. Since voltage of the battery has to be Q over C equivalent, voltage on battery is Q times, this has to be 1 over C equivalent. So the equivalent capacitance of the circuit is just 1 over this thing, or that. So that's why this is true. And again, this is for capacitors that are in series. And the formula looks like the resistors in parallel. So it's just completely reversed for those two. So again, what I want you to get out of this is just to have a little bit of understanding why this might be true, knowing that the charge on all of the capacitors that are in series have to be the same. I think that's it, and now you should have enough information to be able to solve problems where you're putting these circuits together.